turns out that that happens in a scrupulously dry solvent. On the other hand, if your NMR sample has, in addition to forget about D2O, if it has water or acid or base, then actually what you will see is you'll see this turn into a singlet, and this is a quartet, and that's a triplet. So that proton will collapse to a singlet and it will not couple. So if you have water, acid, or base, then coupling with this proton to that CH2 stops. You don't see it. Now the question is, what's going on? I think you kind of know what's going on. If you remember our discussion about hydrogen bonding, right, and our acid-base chemistry. This is an example. And by the way, this happens not just for alcohols, but for any HX. Okay, so anytime you have an electronegative atom X that's bonded to a hydrogen, so that XH is acidic, this can happen. Now, what's going on? Well, the first thing, let's talk about chemistry, what goes on, and then we'll figure out spectroscopy, what's going on. So, if you have acid, same thing with its base, but it's the same thing. I've colored one of these protons red. And so that red proton can engage in acid-base chemistry, right? So this is the base, that's the acid, and then now this is the acid, that's the base, except the red proton, if you follow the red proton, that ends up on the ethanol, and the black one ends up on the hydronium ion. And remember, this is happening many, many times. This is happening very fast. It's happening with lots of different ethanols, lots of different hydronium ions, and so there's rapid exchange of this proton. So this red proton is being exchanged, and it's coming off, it's going on, it's coming off, and it's happening. This process is being repeated all over. Okay, now let me ask you a question. If I have any proton, and let's just pick the ones on the hydronium ion, what can I expect for the spins of those protons? Well, you know that half the time, roughly, they're going to be plus 1/2, and roughly half the time, they're going to be minus 1/2. So this is a small difference between the two. But on average, right, it's, you know, 1,000,000 times they're going to be plus 1/2, and then, or 1,020,000 they'll be plus 1/2, and then 1,000,000 times they'll be minus 1/2. But that's a very small difference. So let's just say that half the time they're going to be plus 1/2, half the time minus 1/2. So that means that on average, this proton, because it's coming off and going on all the time, on average, half the time it's going to be plus 1/2, half the time it's going to be minus 1/2, which means that on average, 0 spin. And on average, 0 coupling. And that's why it's going to show up as a singlet if it's rapidly exchanging, okay? And so, so we know two ways now to wipe out, if you will. Well, in one case it wipes it out completely. D2O wipes this signal out, or, and so there's no splitting, or we can do the rapid exchange, in which case we still see this proton, but there's no splitting. Okay? So both ways we can collapse that triplet, the OH triplet, into either a singlet or we don't see it at all. Now, that introduces us to this concept of signal averaging. Now I mentioned signal averaging in the context of the anisotropic effect that was responsible for the high chemical shift of vinyl protons, right? I said that vinyl protons appear all the way up to 4.5 to 6 or wherever, and that was because of magnetic anisotropy. The induced field of the pi electrons opposing the applied field. And then I said, well, yeah, but this happens only in one orientation of the ethylene or the vinyl group with respect to the external field. How about all the other orientations? I said that, well, because of signal averaging, it averages out, but that one orientation is very important. Now, the take-home lesson is that when we look at signals in the NMR, we're not looking at static molecules. We're looking at molecules that are moving within solution, but also that are undergoing conformational change. And so if I have multiple conformational states of a molecule at room temperature, say, then the NMR that you're going to measure is going to be some average of all of those states. Okay, so how do we know this? Well, okay, so let's take a familiar example. And the example we always like is what? It's cyclohexane, right? Now, if you remember way back when, we talked about the fact that we have two different classes of protons in cyclohexane. We have axial protons and we have equatorial protons. And so these two protons are going to be distereotopic. And they will couple to each other, and but you only see a singlet peak at 1.4 at room temperature. Now, why is that? Well, you already know why that is. That's because at room temperature, that chair-to-chair interconversion is taking place fast. And so what you're seeing at 1.4 ppm is an average of all of those protons. So now the question is, well, okay, that's at room temperature. We know that there's an activation barrier for that chair-to-chair interconversion, which means that if I place that cyclohexane molecule in an environment where it can't get enough energy to do that chair-to-chair interconversion, then I should be able to freeze it, right? I should be able to stop it in one conformation. If that's the case, then I should see axial protons here and equatorial protons there. And in fact, you can do that. Now, the way you do this, however, if you do it in cyclohexane, it's still going to be kind of messy because of the coupling constants. And so what you would like to do is you'd like to design an experiment whereby you see a singlet for the axial and a singlet for the equatorial. And because that will just be an easier experiment to interpret. So the way you do that is as follows. You make this per-deuterated cyclohexane where I need one and only one proton. Okay, and there are ways to do this. We don't need to discuss how. But so I have just one proton. Everything else is deuteria, right? So the deuteria, remember, they have spins. They absorb energy in the NMR, but in a different frequency. So I can do proton NMR, and I will never see the deuteria, which is nice. So now I can take this sample and notice that when it does a chair-to-chair conversion, the equatorial becomes axial. So I can expect a singlet for the equatorial and a singlet for the axial. Now, there's hardly any difference in energy between these two, right? And so at room temperature, you're just going to see that average peak. Now, as you cool it to colder and colder temperatures, something happens. And so at minus 60, you start to see two very broad peaks. So instead of seeing one broad peak, you start to see them separate out. Then as you go lower and lower and lower in temperature, those two broad peaks separate more and sharper. And so when you get to about minus 90, then you see two distinct singlets. Now, why should that be? Well, it means that you have two chemical shift non-equivalent protons. One's the axial, one's the equatorial. And the interconversion is now slow enough that there's no signal averaging. Now, this is, so you can say that, gosh, why would I want to go to this much trouble? And the reason is that you can get some very interesting information from NMR about reactions. And the same thing that we say now for conformational change applies also for reactions, right? So if I stop a reaction from taking place, or if I stop conformational change from taking place, then I have the possibility of observing intermediates that you can't see any other way. And so NMR has proven to be a very useful tool for doing exactly that. Now, this just recapitulates on what I said. You have to recognize that this kind of signal averaging that we saw for the per-deuterated cyclohexane with one proton in, that signal averaging takes place for all molecules at room temperature, right? And or at any temperature during which they can undergo conformational change. And so whenever you record a spectrum of a molecule like this, you're looking at a CH2 and a CH3, but you're looking at averages. You're not looking at the same thing. In the back of the room, can you stop texting, please? Thank you. How many times do I have to say that? I said it's on your syllabus too, right? I said I don't want to see iPads, iPhones, I don't know what's. None of them. Okay? Thank you. So signal averaging is going to take place in all cases. Okay, this again recapitulates what I said, that when you have this proton exchange for exchangeable protons, then half the time that's going to be a plus 1/2, half the time it's going to be minus 1/2. On average, it's going to be 0. And so therefore, no coupling will be observed. And that's why when you add acid or water or base to an alcohol, you end up wiping out the coupling of the exchangeable proton. Okay? And so it's kind of a useful thing to be able to do, because this also will simplify spectra, right? If you have additional coupling, then you can stop it just by doing this exchange. Okay, now what I'd like to talk about next is C13 spectroscopy. And before we get to this, let me ask a question. First of all, you know from our discussion of mass spec that C13 is a rare isotope, right? Does anybody remember roughly how rare? Yeah, okay, so it's you know, it's much less than 1%. Okay, so let's say I have a molecule, you know, obviously carbons. What are the chances that I'm going to have one C13 in there? Well, you can't answer me numerically because I didn't tell you how many carbons there are. Let's say there are 5 carbon atoms, right? So the chances of having any one of those being C13 is going to be the natural abundance raised to the 5th power. Okay, so it's kind of small, right? Now, let me ask you another question. What's the chance, if you have 5 carbon atoms, of that molecule having 2 C13s in it? Okay, now that's a really hard question because there are a number of ways those C13s can be in there, right? They can be next to each other, they can be one separated, and so on, all combinations. But regardless, it's going to be an even smaller number than that very small number raised to the 5th power. And so that's with 5 carbons. With 10 carbons, it's even lower, and so on. So what's the possibility of 2 C13s in any molecule being bonded to each other? Oh, that's essentially 0, right? So here's how it differs. Here's how C13 differs from proton NMR spectroscopy. You know, with protons, because we're looking at the abundant isotope, we're always going to see coupling. But if I have a molecule like this with 5 carbon atoms, then the chances of 2 of these being C13s and coupling is essentially 0. So what I'm going to see is I'm going to see a singlet for this, and a singlet for that, and a singlet for this, and so on. They're all going to be singlets because they don't couple, because the probability is not there. So I say I see a singlet for this. Well, yes, but then in another molecule I'll see a singlet for that, because the same molecule doesn't have 2 C13s, right? And then there's another molecule where this is C13, and there's another molecule where the other carbon, was one, would be a C13. And so I observe singlets and not coupled spectra. Now, it turns out that proton, which is always going to be there, does couple with C13. And so in the C13 spectrum, I said singlet, singlet, singlet. You should say no singlet, because, hey, the protons attached to those carbons, those couple, and they couple with big coupling constants. So you should not see singlets. You should see whatever multiplet you expect from from 1 bond, 2 bond, 3 bond, whatever bond coupling to the proton. And so that would result in a truly ugly spectrum. Well, I shouldn't say ugly. A spectrum with way more information than you can extract easily. Well, okay, so I didn't lie. The C13 spectra are in fact singlets, and the nice thing is, and take a look at this. I mean, the nice thing is that the C13 spectrum spans not from 0 to 12 ppm. This is from 0 to 200. So you get a huge spread in frequencies. And as a result, even an ugly molecule like this, where you have 6 carbon atoms in a row, now the proton NMR for this would definitely, even at about 500 megahertz, that is not going to be first order, I can guarantee it. But look at this. Each and every one of those carbon atoms appears separately. So the C13 NMR can separate carbon atoms very, very nicely. So you get better resolution in a sense than you ever would in a proton NMR spectrum. But they are all singlets when, okay, so A is this. I mean, this, if it couples to just to the protons that it's bonded to, then because the proton has a spin of plus or minus 1/2, that should be a quartet, it's probably going to be coupled to these two, and so these singlets. So how do we do that? Okay, so it's an instrumental technique. So here's what you do with the spectrometer. You have two RF coils. One RF coil gives the frequency that you need to excite the C13 molecules. But there's another RF coil that is always pumping energy into the protons. And so the protons are all being decoupled from the C13s by virtue of having them all pumped up into the high spin state. And so you end up being able to do what's known as a proton decoupled C13 spectra. So all the spectra we're going to see, all the C13 spectra are going to be proton decoupled, and that's just to cut down on the amount of information. Now, okay, so you can kind of see that we're getting good information here, but it turns out extracting that information for carbon is a much more difficult task than it is for protons, and here's why. The NMR equation is given here, and remember that V naught is the external field, and then there's this gamma. This little gamma is a constant of nature called the gyromagnetic ratio. It's a constant for each NMR active nucleus. And here I've shown, please don't memorize numbers, but for C13, gamma is this. For proton, gamma is that. So proton has a much bigger gyromagnetic ratio than does C13. And so this means a couple of things. Now, for practical matters, we don't really care, but it means that the frequency for C13 is 75 megahertz, whereas for the same magnet, this would be 300 megahertz. So you're looking at very different parts of the spectrum. And that's nice because there's no overlap. But there's something else that this causes. And the problem is this, that the sensitivity of the NMR experiment varies as the cube is the power 3 of the gyromagnetic ratio. And so the sensitivity of proton versus C13, or rather, proton versus C13, is going to be given by this number, which turns out to be about 63. So if I take the inverse of that number, then the C13 signal is only about 1.6% as intense as the proton signal. So you say, well, okay, fine, 1.6% is not very much, but that's not that bad, is it? No, it's not. The problem, however, is that C13 has low abundance too. And so when I combine this number with the low abundance of C13, I'm going to multiply these two. That turns out this is the number I have to look at to compare the intensity of a C13 to a proton spectrum. That means that at natural abundance, I'm only going to get, what is that? This is 1 per 1,000. This is 1.75 per 10,000. So it's almost 10,000 times less, a little more than 10,000 times, less sensitive than the proton spectrum. So that creates a problem, right? Because I can't make my C13 NMR sample 10,000 times more concentrated than the proton sample. I just can't stuff that much material into that tiny NMR tube. And so I can't do it that way. I've got to do it in a more clever way. Now, in the old days, before computers were cheap and fast, here's how they did it. They had computers that just weren't very good. And so you take a spectrum, okay, C13 spectrum, you see a bunch of noise, noise. And maybe here, this little tiny peak that sticks out of the noise, right? And that's the strongest peak. The other weak peaks, you don't even see them. And then you take another spectrum, you want the spectrum, and there's just maybe a little bit of there, and then you see a little bit there, and you keep going, keep doing it. Now what you do is after you've done this, about literally 10,000 times, you take all these spectra and then you add them up. Now you say, why is that going to work? Here's why it works. Because if I have a peak here, then in every spectrum, I'm going to see that peak. If it's noise, then in some spectra, the noise will be going above the baseline, and some spectra will be going below. It's random. So if it's random noise, it's going to cancel out to 0. So once you add all of those spectra, then you'll see real peaks, and the noise will all average out to 0 because the noise is random and the peaks are discrete. Okay? So that's a common instrumental technique, not just for NMR, right? And so, but it takes time because let's say it takes a minute to scan the spectrum, then another minute for the next one, and another minute, pretty soon 10,000 minutes, talking real time. And so that meant that if you had a C13 spectrum to run in the bad old days, it was an overnight run, which meant that you tied up one NMR spectrometer for 12 hours or so. And so it turns out that there's another technique that's very nicely described, I think, in your solutions manual called Fourier transform NMR. I'm not qualified to explain the details of Fourier transform, but here's how it works. You end up sampling all these frequencies at once. So you don't have to sample this one and then this one and then this one and then you take your whole time. You sample everything all at once, and then mathematically you can deconvolute the Fourier transform to get back to your spectrum. You can add those Fourier transforms, and so it cuts down greatly on the time for acquisition of a C13 spectrum. So now, even using not the most sophisticated machine, or not using using a fairly dilute sample, you can get decent C13 spectra in under 5 minutes. That's a real revolution, and it depended on development of fast computers. And that's how you get around the sensitivity problem. The sensitivity problem is real. And so, getting a C13 spectrum still takes longer, and it's harder than a proton, but you can still do it. Okay, now, I said something about decoupling the protons from the C13. This is always going to be a problem if you have two NMR active nuclei in the same molecule. So let's say that you have protons and fluorines. Okay, so fluorine and proton absorb in different parts of the spectrum. So when you run the proton spectrum, you're not going to see the fluorine peaks. But what you will see is the proton-fluorine coupling. Likewise, if you run a fluorine spectrum, the fluorine peaks absorb a different area than the protons, but you will see the fluorine-hydrogen coupling. And so that is usually not a very big problem with fluorines, but with the C13 it is, and that's why you do this proton decoupling business to wipe out that proton coupling. So C13 has, however, some very unique advantages, and I kind of hinted at one. I told you one. And because of the low abundance, natural abundance, you never observe C13 splitting. The reason is the one that you already told me. 1.1%, the chance of having two of these C13s in the same molecule becomes, for practical reasons, practical purposes, zero. So you don't see C13 coupling. And so each peak appears as a singlet after it's been decoupled. And then the other thing is, I also mentioned, the range of chemical shifts is very, very wide when compared to a proton. So you can see usually you can see each and every carbon atom, even in a complicated molecule. So what the C13 spectrum will very often allow you to do is count up carbon atoms. Now you know what the carbon count is. And that's actually very, very useful. Also, I don't know if you can read these numbers, but I've shown a methine, a methylene, and a methyl, and I've shown their chemical shifts. And you'll notice that that the quaternary, tertiary, secondary, and methyl, they all follow the same trend that you expect for protons that are methyl, secondary, tertiary, and so on. And so carbon shifts kind of follow the same trend that you saw for protons. Okay, now we've got two kinds of information from proton spectra. Let me go back to the very, very first spectrum I showed you in proton NMR and remind you of what that was. Remember the dimethoxymethane, right? And we said that we get we get more than two kinds of information. But remember the integral? Remember that the area under this peak was proportional to the hydrogens or the protons that were responsible for ion absorption? Okay, so the areas under these peaks are going to be proportional. In this case, 6 to 2, or 3 to 1, if you will. And that gives us useful information. Now, it turns out you don't get that from C13 for reasons I don't need to explain right now. But it turns out that the areas under the peaks for C13 are not proportional to the number of carbon atoms leaving them. However, the peak heights, if you will, the integral, the peak heights, the relative peak heights still give you some information. Here's why. Because if you have, let's see if we can see it here. No, we'll see it in the next one. Okay, so let me show you what I'm talking about. Here's camphor. Okay, so I want to show you this peak here and that one. Okay, so these carbons are all of the carbons in camphor are distinct. Each one gives a different signal. And you'll notice that this one and this one are the furthest downfield. And so the most deshielded ones are these two, which is what I already told you. But the other thing you'll notice is that they're the smallest peaks. These are tiny little peaks. So if you have a carbon atom, the number of protons attached to it will be revealed sort of by the intensity. So if there are no protons attached to that carbon atom, then the intensity will be low. And so carbon atoms that don't have attached protons are weak, give you weak signals in the C13. So you can actually get some information out of the C13 that way. Now, another place where it's useful is in isomer counting. We're going to see that. So carbon atoms with lots of protons attached, like methyls, give you strong peaks. Carbon atoms with no hydrogens attached give weak peaks. And certainly carbonyls fall into that category. So not just quaternary carbons, but also carbonyls. No protons, weak peak. Now, one place where C13 really shines is determining the presence of isomers on the basis of the numbers of peaks. Okay, so if you have 3 isomers, and I've just given you the 3 possible isomers of dihydroxybenzene. 3 isomers of dihydroxybenzene are in 3 NMR tubes, and you can run C13s. How do you tell which is which? How do you distinguish, those 3? Well, from C13s, it's very, very simple. Here's how. Just as we had for protons, we have a simplifying effect of symmetry, right? So we look at these 3 dihydroxybenzenes. They all have a symmetry element, and the symmetry element you're looking for is a plane. So if I look at the 1,2-dihydroxybenzene, there's a plane that runs right down the middle here, right? If I look at the 1,3-dihydroxy, there's a plane that runs through here. If I look at the 1,4-dihydroxy, it runs that way, right? Now there's another one that runs this way too, but let's just look at that one. Okay, so each one of these dihydroxybenzenes is in fact symmetrical. Now, because of that, we should be able to see that this carbon atom and that one are identical as far as the NMR is concerned, right? So the 2 ones that are bonded to the hydroxys are going to be the same. Why is that? Well, because I can apply my little chemical equivalence, stereochemical equivalence test, color one of them red, and so on, and that will reveal that these 2 are chemical shift equivalent, as are these 2, as are those 2. So how many peaks total do you expect for this isomer? 3. Okay, so now tell me how many you expect for this one. Think. Remember that the symmetry runs right through there. 4. 1, 2, 3, 4. How about for this one? Think. Don't just. I heard it, 2. So these are identical, these are identical, right? So this is highly similar. You only see 2 peaks for this one, 4 and 3. So, simple, right? You just run C13 spectra. Don't even worry about chemical shifts. You don't need to do that. Don't worry about coupling constants in the proton. Don't do anything, just count lines. So it's very, very useful for doing exactly that kind of isomer separation, identification. Now, NMR is a big area. It's not my specialty. There are a lot of experiments that you can do that will reveal carbon connectivity in a molecule. So you can actually do experiments. These are some of them are called two-dimensional experiments. So instead of having a peak or a spectrum that looks like the ones you see, you'll have peaks all over an area. So you can have the protons here and the C13s there. You can see correlations between a proton signal here and the C13 signal there. So you tell that this proton is attached to that C13 and so on. These are sophisticated experiments beyond anything we need to know now. But there's one experiment which your book talks about that is really good, really useful. That's the depth experiment. Distortionless enhancement of fluorescence. It's got some kind of acronym. This is illustrated for camphor. Basically what this does is it gives you a separate NMR, C13 spectrum for methyls, for CH2s, and for methynes. And so you don't see these two. What you do see is you see the methine. Methine has a single hydrogen. There's only one methine carbon. That's this one back here. There's a hydrogen back there. So that's this peak. And for methylenes, you have 1, 2, 3 methylene peaks. And for methyls, you have 3. So you can tell in the C13 NMR which are the methyls, which are the methylenes, which are the methynes, and that allows you very often to determine structure. So this is a really useful technique. You don't see it you won't see it in the undergraduate lab, but it's useful because it gives you separate spectra for these kinds of carbon atoms. And so the carbon atoms that we said have no protons, those don't appear in the depth experiment. That's just one of many, many different kinds of experiments that one can use to tease out information from any molecule that has carbon or proton. Now, there's another way to use NMR that I kind of told you a little bit about the last time. Let me try to illustrate this, especially for the people who may have a biology bent. So let's just say that I have a protein, right? And protein has different R groups here. Proteins have this structure. This could be R1, this could be R2, and so on. And the protein's a long molecule of a mid bond. So this would be, each one of these is an alpha amino acid amid. And let's just say that I want to do protein structure. So how do I do that? Well, one way, as I said, is to feed the organism compounds that have one of these amino acids labeled with the C13. So in other words, I could have the organism produce a compound like this, right? There's a hydrogen there, but you don't need to worry about that. And so when I run the C13 spectrum for this particular protein, what I will see is I'll see that peak and nothing else, because if it's been enriched, then even if it's a low level of enrichment, you can be absolutely sure that it's going to be there at more than 1.1%. And so I'll see a huge enhancement of that peak. So I will know then in my protein NMR spectrum that, that signal is due to this particular amino acid. And you can do that actually not all that hard. I mean, it's not always easy, but it's not a difficult experiment to do. The problem is getting high levels of enrichment. There are techniques for that. So you can use this, and it is used for determining structure of actually large, difficult molecules. Okay, now, in the time we have remaining, I would like to go over some of the high points of this chapter. It's a hard chapter. And spectroscopy is different from everything else that we've talked about. I know that. You have to make the effort to do problems. The problems at the end of the chapter are good. We've got some really good problems there. I suggested, some of them. The ones I did suggest doesn't mean they're no good. It's just I thought my judgment, the ones I suggested, were better. Do those problems and get in the habit of getting information out of those spectra. The first time you confront these spectra, they look intimidating. There's a lot of information there, and you have to go through some mental manipulation to get that information and translate it from lines on a page to a chemical structure. So you have to do that a few times before it becomes second nature. But once you do that, I think you're going to appreciate just how powerful these techniques are. There are no words to explain how difficult organic chemistry was before spectroscopy. People of my generation, we can't even imagine what people did in the up until the 1950s and 60s. The first commercial NMR machine came out in 1960. Okay, so it's not that old. The technology is not that old. And yet, before 1960, people did some really nice, complicated work. And if you think about how they did that, it's actually mind-blowing. I don't know how they did it. It's just labor-intensive beyond belief. Okay, so NMR spectroscopy, and now we're going to talk about proton NMR spectroscopy, depends on this property, this quantum mechanical property of nuclei, certain nuclei, but protons, C13s, fluorine-19, and so on, that is called spin. And what that does is it gives you the opportunity to allow the molecule to absorb energy by placing the molecule within the field of a very strong magnet. In other words, the two spin states for proton have identical energies in the absence of a strong magnetic field. The magnetic field gets stronger and stronger and stronger. The energy states of those two spins gets larger and larger. Now, because you're looking at a very small number of electronically excited protons, and the energy difference is actually very, very small, you need to magnify it as much as you can. Because of the NMR equation, it turns out, which is this thing here, it turns out that the difference in energy is proportional to this. All of this is a constant. The only thing you have to play with is the magnetic field strength. If you don't have a strong magnetic field, then this becomes a very small energy difference, and you don't see much change. But in the presence of a strong field, then the plus and minus 1/2 spins actually have enough energy difference that you can do the experiment. And so it turns out, what is a strong field? Well, strong field is about 70,000 Gauss. And at 70,000 Gauss, if you plug in the number into that equation, it turns out that you're looking at around 300 megahertz. So the 300 megahertz corresponds to the frequency of the radiation that you need to excite those spins. Okay, so the nice thing about proton NMR is that it gives you different kinds of information. And the information that it gives you are the following. You get something from the chemical shift. And so let me show a spectrum here. So let's look at ethyl bromide, which is a simple spectrum. So chemical shift is where in the spectrum the peaks absorb. Remember that the peaks that absorb in this part of the spectrum are deshielded, which means that they are either bonded to an electronegative atom, or there's something like what we saw going on in pi bonds, where you have magnetic anisotropy, but they are deshielded, which means that they're experiencing a strong magnetic field. Or if in this part of the spectrum, they're shielded. So the chemical shift tells you something about the chemical environment. There are tables of chemical shifts, Please don't memorize them, but use them when you solve the problems that will tell you, for example, if I have a proton like this, where the CH2 is bonded to a bromine, where do I expect that to appear? And it turns out this is roughly where you expect it. So you get information from chemical shift. The other kind of information you get is from the integral. The integral, remember, gives you the area under the peak, which is proportional to the number of protons. It doesn't give you the absolute number of protons, but it gives you the ratio of protons. So in this case, 2 to 3. That's very useful information. And the third kind of information is this spin-spin splitting business. So you'll notice that here, this peak, this is just an enlargement, this is an enlargement, a quartet and a triplet. That is the n+1 rule. Why is this a triplet? Well, this is a triplet because 2 plus 1 is 3, and it has 2 nearest neighbors. This is a quartet because 3 plus 1 is 4, it has 3 nearest neighbors. And so from those 3 kinds of information, you get really very detailed structural information about your molecule. I mean, think about infrared. Infrared doesn't do anything close to this detail. Neither does mass spec. Not saying that you don't get useful information from mass spec or from infrared. Clearly you do, but it doesn't give you this kind of detailed structural information that you get from NMR. So this is why it is such a useful tool. Now, those nice triplets and quartets appear in first-order spectra. And I showed you also some non-first order spectra. You saw that when the difference in chemical shift measured in hertz is not much different than the difference in than the coupling constant of protons, also in hertz. But then those spectra don't show up nice the way I just showed you, but you end up with complicated jumbles of peaks that are impossible to interpret. And then I told you how you can get around that problem. The way you get around that problem is to run the spectrum on a stronger magnet instrument. So you take your sample to a 600 megahertz. Now, the difference in chemical shift, measured in hertz, becomes bigger. And so maybe the peaks will resolve and they'll become first order. And so there's a big incentive then to build bigger and bigger and bigger magnets. Now, this works very well, but remember that these magnets are electromagnets and that they require superconducting materials. These are superconductors that are stored in a Dewar, a thermos flask. The thermos flask is kept at ultra low temperature, usually liquid helium. And if it gets much higher than liquid helium temperature, then the superconductivity disappears and you don't have a magnet anymore. And so these are an engineering feat. They also require fairly large amounts of helium. I asked you to take a look and see where helium comes from. Did anybody do that? You go to Safeway, you get those shiny balloons, you empty them, you know, it's like. Okay, so this is, so maintaining a helium supply is maybe a bit of a challenge in the future. So the electronegative atoms de-shield protons and adjacent carbon atoms. And so remember there was a correlation, very strong and good correlation between electronegativity and chemical shift. So more electronegative fluorine means it de-shields the methyl group much more than the less electronegative iodine. So methyl fluoride 4.6, methyl iodide 2.16 ppm. And so this is the kind of correlation that allows you to determine structure, because these effects are also additive. So if there are 2 chlorines or 3 fluorines, the effect of each chlorine de-shields the proton more and more and more. And you can say, well, how do I know that? Well, you can look at tables. I mentioned to you that there's a very nice table in your solutions manual that gives you, that allows you to make predictions about CH2 groups that are bonded to 2 different groups that de-shield them. That kind of information is quite easily accessible. Okay, now the hard part, and here's where you really do need to go back and review, is figuring out the number of absorptions in a NMR spectrum. We did that today for the C13 when I asked you about the isomer counting. And for that C13 experiment, I think from what I detected from the class, you guys kind of saw pretty easily how to do that. It's a little bit harder for protons. So first of all, if protons are not constitutionally equivalent, then they're not going to be chemical shift equivalent either. And so if they're not constitutionally equivalent, you know that they're going to have separate peaks. Okay, so that's the easy part. But now, let's say that they are not they're constitutionally equivalent. So if they're homotopic, they're going to have the same chemical shift. What protons are homotopic? Which example did we give for homotopic protons way back when? And how did we tell? Methyls, right. And so remember, you take say methanol, and you take 2 of the protons in methanol's methyl group, color one of them red, then color the other one red. Take a look at those two colored methanol molecules. If they are identical, as they are, then those 2 protons are homotopic. Homotopic protons don't couple to each other, and they always have the same chemical shift. And enantiotopic protons, we illustrated that with the methylene group of ethanol. So you take one of the protons of the CH2 of ethanol, color it red, then take the other one, color it red, compare those 2 colored ethanol molecules, those are enantiomers. Enantiotopic protons are going to be chemical shift equivalent, except in that very rare case where I have an asymmetric NMR solvent or a chiral NMR solvent, i.e. never. So enantiotopic protons are going to be chemical shift equivalent essentially all the time. Now the ones where it's hard are distereotopic protons. So distereotopic protons, those are probably going to be chemical shift non-equivalent every time. Now, I hedge. Why do I hedge? Well, because accidentally, they could have the same chemical shift. In other words, if I have a weak magnet, or if I'm just unlucky, then those 2 distereotopic protons may just show up under the same peak. So remember, these 2 are distereotopic. This is the example I gave last time, right? Because if I color one of these, and then I color the other one, those 2 molecules are going to be diastereomers. Because why? Because this is an asymmetric center. Because this is chlorine different from methyl, different from hydrogen, different from ethyl. So I have one asymmetric center here. By coloring one of these hydrogens, I made a second one. And so each one of those 2 isomers are going to be diastereomers. Therefore, the 2 protons are diastereotopic. Therefore, these 2 protons are not going to be chemical shift equivalent. And they will couple. So what's this one going to be? Well, it's going to be double it here, it's going to be double it there, and it's going to be quartet. So it's a DBQ. And so, yeah, proton NMR is a little bit tricky, and you do need to review that chapter 10 material on stereochemical and chemical equivalence. Okay, so problem solving. The one thing your book does not remind you is that you need to, the first thing you need to do when the problem uses the empirical formula, figure out units of unsaturation. Okay, so go back, take a look at that formula that we have for units of unsaturation. It's the first thing you do when you have an empirical formula. And then you go through this routine and figuring out how many non-equivalent protons, the integrals, chemical shifts, and then come up with partial structures. So the key is not to look at all the material, don't write anything down and say, aha, I know what it is. If you can do that, you're really, really good. Most people can't. And so what you do is you write down the little partial structures and then kind of join them together in every which way possible, figure out which one makes sense and which one doesn't. There's several experiments, several questions in the chapter that ask you to do that. Okay, so we'll pick up the next chapter on the